This is the final demonstrator of the fabulous project implemented at the Photon Lab of Istituto Superiore Mario Boella of Turin, Italy. In particular, it is composed by an optical line terminal, an optical distribution network, and two optical network units, and it is programmed in order to support the simultaneous transmission of two bidirectional Ethernet signals, one for each optical network unit. The optical line terminal is composed by two main parts: an electronic core, which includes an FPGA, a digital-to-analog converter, and an analog-to-digital converter for both the real-time signal generation and signal processing, and the optical front end, composed by all the optoelectronic devices needed for the optical signal transmission and detection. In particular, the downstream signal generated by the FPGA drives this Mach-Zehnder modulator connected to an external DFB laser working in the L band. This way, the FDM downstream signal is ready to be transmitted through the optical distribution network. The FDMA upstream signals coming from the ONUs are detected by this optical coherent receiver, whose outputs are provided to these electrical IQ demodulators, then to this low-pass filtering stage, and finally to the analog-to-digital converter and the FPGA for the real-time processing. The local oscillator, connected to the IQ demodulators, is set to the FDMA frequency assigned to the channel to be detected, while the coherent receiver's local oscillator is the same C-band laser used to feed the reflective optical network units. To complete our OLT, we have these two EDFAs. The first one is used to set the right upstream launch power, while the second one is used as a pre-amplifier for the upstream signal detection. Inside this black box, we place the polarization beam splitter, the bandpass optical filter, and the variable optical attenuators needed to correctly manage the upstream signal transmission and detection. Finally, a C-band L-band optical filter is used to combine the optical downstream and upstream signals into a single fiber. The optical distribution network is composed by 25 kilometers of single-mode fiber, a variable optical attenuator used to increase the overall ODN loss, and an optical splitter used to connect the two ONUs. The first ONU is composed by discrete components, and it is fully equipped to correctly manage both the upstream and downstream signals, which are separated by this L-band C-band filter. The downstream signal is provided to this avalanche photodiode, whose output is provided to the real-time FPGA. The unmodulated upstream wavelength generated at the OLT is amplified by the semiconductor optical amplifier we package into this box, reflected and modulated by this reflective Mach-Zehnder modulator, and transmitted back towards the OLT. The upstream signal is generated by the FPGA followed by this electrical IQ modulator, whose local oscillator is set to the FDMA frequency assigned to this ONU. The most important device of our second ONU is the reflective Mach-Zehnder modulator integrated in the silicon photonic platform realized in SEALETI during Fabulous project. The main purpose of this ONU is to demonstrate the performances of this device, therefore it is focused on the upstream transmission only. Again, an FPGA and an electrical IQ modulator are used to generate a signal that modulates the upstream wavelength coming from the OLT thanks to the integrated modulator. Since this prototype does not include the 3.5 semiconductor optical amplifiers, we used an external amplifier placed in front of the modulator. With this measurement, we demonstrate that the first ONU is able to correctly generate the upstream signal, evaluating the related electrical spectrum at the OLT receiver's output and the bit error rate measured in real time with the OLT FPGA. Starting with 17 dB of ODN loss, including the fiber and the splitter, thanks to our real-time error counter, we measure a bit error rate of about 10 to the minus 8, and since the FEC we implemented in our FPGA requires a bit error rate lower than 10 to the minus 4 to work correctly, we are quite far from this threshold. Of course, if we detach the fiber, the connection is lost, but it is recovered as soon as we reconnect it and we reset the FPGA. We then gradually increase the ODN loss and accordingly the bias current of the SOA, and we verify that with this ONU the upstream signal can be correctly detected up to an ODN loss of about 30 dB before reaching the prefect Baird threshold of 10 to the minus 4. We then repeat the same measurement with our second ONU, the one with the integrated Mach-Zehnder modulator. We start again from 17 dB of ODN loss, and this time we measure a bit error rate of about 10 to the minus 7. We again increase the ODN loss and accordingly the bias current of the SOA, and we verify that with this ONU the upstream signal can be correctly detected up to an ODN loss of about 21 dB before the effect threshold is reached. We then simultaneously switch on both ONUs, setting their FDMA frequencies in order to avoid to interfere one to each other, as shown in the electrical spectrum analyzer connected to the OLT coherent receiver's output. And we demonstrate that the OLT is able to correctly detect both of them simply by changing the local oscillator connected to the electrical IQ demodulators. In particular, when the local oscillator is set to the frequency assigned to the second ONU, in this case 1.75 GHz, we detect the bit error rate of the signal coming from the second ONU, while if we want to detect the signal coming from the first ONU, we just need to set the local oscillator at the OLT to the frequency assigned to the first ONU, in this case 2.2 GHz. Of course, if we reduce too much the frequency spacing between the two FDMA channels, as for example moving the second ONU to 2 GHz, the bit error rate of the channel under test is strongly affected, since we have a strong adjacent channel interference. In order to minimize this interference, it is sufficient to set the frequency spacing between the two channels equal to the channel's electrical bandwidth, in this case 330 MHz, obtaining again the bit error rate we measured before.